going to look at the history of the atom. One of the reasons we look at it and study how we came about our current model of the atom is because it's a very good test model or case study of how science works and the methods that scientists go through to understand things that they can't see and come up with models based on evidence that they collect. Now, with the history of the atom, we have to understand that we came about our current model using two things. One, much of the information that we have was done around early 1900, just before and up until 1920. Two, a lot of the information was done looking at how electricity and atoms interact. And so they would look at how the interaction between electricity and atoms. And three, we looked at the interaction of light, energy, but specifically in the form of light, and how both of these allowed us to not only determine what parts make up an atom, but where these parts are located. Okay? And when we were looking at light and investigating the fundamental particles, it allowed us to also understand the chemical and physical properties of an atom. Now, we had some ancient ideas of the atom. The first one was by Democritus, and he proposed the idea of an atom, and he said that they were the smallest divisible part, that the atoms came in different sizes, constant motion, and they were separated by empty space. His ideas, even though he didn't have anything to work with, stand up to the test of time. However, there was also another ancient Greek who was much more respected, and as a result, his ideas were the ones that were pervasive until for about 2,000 years. And he rejected the idea of an atom and said that matter was composed of four basic substances: earth, fire, water, and air, with different qualities that gave the different types of matter their chemical and physical properties. Now, this idea that matter was made up of earth, fire, water, and air started to be debunked when scientists started to apply electricity to compounds. And when they started applying electricity to compounds, this allowed them to break them up into elements. So, for example, they would take a piece of rock and they would heat it up to melt it, and then apply electricity to it. And in the process, Humphrey was able to discover a lot of our alkali metals, so calcium, magnesium, beryllium. He also discovered potassium, sodium, lithium. He discovered chlorine. Okay, and so because he showed matter could be broken down in predictable ways, this suggested that Aristotle's ideas that there were only four fundamental particles that were composed in different ways was not correct. And so scientists had to start coming up with other ideas. Okay. Our first individual who started us on the modern atomic theory was Dalton. Dalton was a child prodigy, and at a very young age, he was leading his classes, teaching them. And when he was in his early 40s, after several years of study, he wrote a book on chemistry, and in it, he had 5 pages where he proposed the model of an atom. And he didn't tell us anything about the structure of the atom itself, just that compounds or elements were composed of atoms, and that atoms could come together to form different things. So there are 5 points to his model. Okay? Elements are made of extremely small particles called atoms, and he brought back Democritus's word. Atoms of a given element are identical in mass and other properties. Atoms of different elements differ in mass, size, and other properties. Again, similar to what Democritus said. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form chemical compounds. This is based off of the work of Humphrey, where Humphrey showed that if he broke stuff down, he would get consistent ratios of different things. In chemical reactions, atoms are combined, separated, or rearranged. Again, a reflection of work that people like Humphreys and Faraday and a whole bunch of other people were doing. Incidentally, Dalton's ideas, even though he made these relatively early on and did not have anything to work with to explain it, hold up to the test of time, except for his third postulate, the fact that they cannot be created, destroyed, or subdivided. because we know that we can now do this in nuclear fusion and nuclear fission. Okay, so Dalton's model is called a billiard ball model because it just says atoms exist. It tells me nothing about the structure of the atom itself or what I would expect to find on the inside. It just tells me that atoms exist. Now, his ideas of atoms existing were resisted for a long time, and a lot of the people in physics and chemistry didn't believe his ideas, and it took a long time. It took almost 200 years till it was finally shown that atoms existed, and it was done by Einstein using Brownian motion. If you ever want to see Brownian motion, sit in a window where light is coming in and you see dust particles in the air. And if you see the random motion of the dust particles in the air, this is Brownian motion. Okay? Einstein looked at pollen being moved in water. If you ever look at pepper in water under a microscope, you would see this as well. And so because of Einstein's work, he showed that atoms did exist. But Einstein wasn't the true champion of the atom. Einstein did work on the atom and did contribute a lot to our more modern theory, but he did not say anything about what atoms were made up of. He talked about their structure of the components of an atom, but he didn't look at how they were made or what went into making them. The real champion of the atom and one of the big drivers behind the structure of the atom was Rutherford. Rutherford was involved with many of the players, either as a student or working in their lab or the director of the lab that individuals worked in to discover these parts of an atom. So, the first part of an atom was developed by Thomson. Thomson's model is called the plum pudding model. Now, around the time of Thomson, so we're looking at around 1895 or so, a number of people had been working with cathode ray tubes. A cathode ray tube is a closed tube on both ends that has electrodes in it so that they can pass electricity through it. And sometimes they would take this tube and they would have a gas in there, and sometimes they would attach a vacuum to it and they would take all of the gas out and they would have a vacuum. And what they found was if there was a gas in here, then the gas would glow if they passed large amounts of electricity through this circuit. But if they took the gas out, then what happens is that the one end of the tube would glow. And so this allowed them to do a number of different studies with this. And so Thomson repeated some of the work of Crookes, but also devised a series of experiments using the cathode ray tube himself. And so this is an case of where the technology allowed the science to occur. They could not do the science till the technology caught up. And so by playing around with the technology, they come across a series of discoveries, and then Thomson came up with a model to explain it. Okay, so what he did was he took his cathode ray tube and he had a number of different things. He put an object in front of it, in the middle of it. He had a magnet, and he had it pass through a magnet, and he had a charged plate, and then he had like a little paddle wheel. And these different things told him different things. The first study, the fact that if I block the path of it, it showed that it traveled in a straight line, and so I could block his path. And this was pivotal for his other next set of experiments, where he showed that he could bend the path with either a magnetic field or charged plates. Since the path bent as in response to magnetic field or charged plates, this told him that whatever was in this tube traveling, it must have had a negative charge. So now he knew that the entity in the cathode ray tube had a negative charge. The question was whether or not it had a mass. And so by placing a paddle wheel in it, and the fact that when it hit the paddle wheel, it caused it to turn, that told him that the particle had mass. So now he had indications that it was a negatively charged particle with mass. And so he took this information and he eventually called it an electron. He had another name before, but finally the name electron was settled upon. Now he knew because atoms were neutral, if I have a negatively charged particle, I have to have positive charged particles to cancel it out. So we said that the atom must be a positive sphere in which these negative particles were embedded. And a positive portion of the atom was spread out evenly, and I had my negative particles with mass placed within it. And they called the model the plum pudding model because it looked like a popular dessert at the time. We might call it nowadays a chocolate chip cookie model. And so here's a picture of the model. We can see our atom. Well, the blue represents all the positive material. We can see that it's spread out evenly. And within my positive material, I have my negatively charged electrons, which are my red spheres. So Thomson was running the Cavendish labs. And for a while, a guy by the name of Rutherford, who we talked about before being the real champion of the atom, worked in Thomson's lab. Then Rutherford, for a little while, went to work at other labs, but near the end of his career ended up taking over the Cavendish labs from Thomson. The Cavendish labs was one of the most famous labs in England at the time. Okay, so let's